Modern bridge construction has reached new heights of efficiency, quality, and durability, largely due to the adoption of innovative methods and advanced machinery, particularly in the use of precast concrete elements. By leveraging precast, prestressed, and post-tensioned concrete components, engineers are transforming the bridge building landscape, significantly cutting down on time and costs while enhancing structural integrity and safety. This approach relies on standardized elements that can be manufactured in controlled environments, transported to the construction site, and quickly assembled, allowing for rapid project completion even in challenging conditions. Precast concrete elements. The cornerstone of modern bridge construction, the precast concrete method involves manufacturing bridge components, such as beams, slabs, girders, and pylons, in off-site facilities. This process allows for strict quality control, ensuring each element meets the precise specifications required for the bridge's design. Because precast concrete elements are created in a controlled environment, factors such as temperature, humidity, and curing times are carefully monitored, resulting in higher quality and more durable components compared to those cast on site. These elements are often either pre-stressed or post-tensioned, depending on the structural requirements, to provide additional strength and flexibility, which is especially useful in bridges that need to withstand heavy loads or seismic activity. Prestressing and post-tensioning are key techniques within this method, both used to increase the load-bearing capacity of the concrete elements. Pre-stressed concrete involves pre-tensioning the steel reinforcement before pouring the concrete, which creates compression that counteracts the tensile forces the structure will face in use. This technique is advantageous for bridge construction because it enhances the durability and longevity of the structure, making it resilient against the stresses of heavy traffic and environmental conditions. On the other hand, post-tensioning involves reinforcing the concrete after it has hardened. Steel tendons are threaded through ducts within the concrete and then tensioned, which applies compression across the element. This method is particularly beneficial in longer spans and when additional flexibility is required, as it allows for adjustments to be made on-site to accommodate specific structural requirements. Advanced machinery and equipment in precast bridge construction. The shift toward precast concrete elements in bridge construction has been supported by the development of specialized heavy machinery that enables efficient handling, transportation, and assembly of these components. This machinery includes gantry cranes, launching girders, mobile cranes, and crawler cranes, each essential in various stages of bridge assembly. 1. Gantry cranes. These cranes are often used to lift heavy precast elements from the fabrication site and onto transport trucks. At the construction site, gantry cranes play a crucial role in positioning these components accurately. Gantry cranes can move massive concrete beams and girders with minimal deviation, ensuring precise alignment for installation. Their ability to lift heavy loads and move along predetermined paths makes gantry cranes indispensable in precast bridge construction, especially in urban settings where space is limited. 2. Launching girders. For bridges built over water bodies or difficult terrains, launching girders are invaluable. These machines are used to position and install precast concrete segments directly over the supports without the need for additional scaffolding or support structures. Launching girders provide stability and precision, placing bridge segments across long spans with minimal human intervention. The use of launching girders drastically reduces the construction timeline and eliminates the need for temporary supports, which reduces both labor costs and environmental impact. 3. Crawler cranes and mobile cranes. These cranes are essential for maneuvering precast components on site, particularly in projects where the terrain is uneven or space is constrained. Crawler cranes provide stability on rough surfaces, allowing for the safe transportation and installation of heavy bridge segments. Mobile cranes offer versatility and can be quickly deployed across the construction site, adapting to various lifting needs. They are particularly useful for smaller components and finishing touches, providing flexibility that complements the efficiency of larger fixed machinery. 4. Transportation equipment. Specialized transport vehicles are also crucial in precast bridge construction. Self-propelled modular transporters, SPMTs, and multi-axle trailers are often used to carry the heavy, oversized concrete elements from the precasting yard to the bridge site. These vehicles are equipped with advanced suspension systems that minimize vibrations during transport, preventing structural damage to the precast elements. Additionally, SPMTs are highly maneuverable and can operate in confined spaces, making them ideal for urban bridge projects. Standardization and quality control in precast bridge construction. The standardization of precast elements is one of the most significant factors in reducing costs and time in modern bridge construction. By using standardized molds and specifications, precast manufacturers can produce large quantities of identical bridge components that can be assembled quickly and seamlessly on site. Standardization not only accelerates production, but also ensures a uniform level of quality across all components, enhancing the overall durability and safety of the structure. In precast facilities, elements are manufactured under strict quality control conditions, which includes monitoring the concrete mix, curing process, and reinforcement placement. Each element is tested for strength, durability, and dimensional accuracy before being transported to the construction site, ensuring that it meets the necessary safety and performance standards. This controlled production environment allows for the use of advanced materials, such as high-performance concrete, HPC, and ultra-high-performance concrete, UHPC, which offer superior strength, resistance to environmental degradation, and longer service life. These materials are often used in critical areas of the bridge, such as the deck and supports, where durability is paramount. On-site assembly and installation process. Once the precast elements arrive at the construction site, the installation process is highly efficient due to the use of advanced machinery and pre-planned assembly techniques. The process usually follows a well-coordinated sequence, beginning with the placement of foundational elements and moving systematically to the bridge deck. Segmental construction techniques are commonly used, where individual segments are assembled one by one, either horizontally or vertically, depending on the bridge design. During assembly, precision alignment is crucial, and the use of laser-guided equipment ensures that each precast element is positioned with high accuracy. Automated and semi-automated machinery plays a role in maintaining alignment, reducing the margin of error and minimizing human intervention. This reduces the likelihood of delays and costly rework, as each piece is installed exactly according to the design specifications. For larger projects, the incremental launching method may be employed. In this technique, the bridge is constructed in sections behind one of the abutments and then pushed forward across the supports incrementally. This method is particularly useful in areas where traditional scaffolding is impractical or environmentally damaging. Incremental launching relies on hydraulic jacks to push each section of the bridge forward, with each segment supported by temporary bearings that guide it into position. Once the section is correctly positioned, it is permanently fixed to the previous segment, creating a seamless and stable structure. Advantages of precast concrete elements in bridge construction. Using precast concrete elements offers numerous benefits, making it a preferred method in modern bridge construction. Time efficiency is one of the most significant advantages, as the simultaneous production of elements off-site allows for rapid assembly on-site, reducing overall project timelines. This accelerated process is particularly advantageous in projects with tight deadlines, such as urban infrastructure upgrades or emergency bridge repairs. Cost savings are also considerable, as standardized precast components are often more economical than custom cast elements. By reducing the need for on-site casting, labor costs decrease and fewer resources are required for materials handling and temporary support structures. Additionally, because precast elements are manufactured in controlled environments, there is less material waste, further contributing to cost savings and environmental sustainability. The durability and longevity of precast, prestressed, and post-tensioned concrete elements are significant advantages as well. These components are highly resistant to cracking, corrosion, and weathering, which reduces the need for ongoing maintenance and repairs. This durability is especially beneficial in bridges located in harsh environments, such as coastal areas or regions with extreme temperature fluctuations, as it extends the lifespan of the structure and reduces life cycle costs. Case studies of precast bridge construction. Several notable bridge projects around the world exemplify the effectiveness of precast concrete elements and modern construction methods. The Hong Kong-Zhuhai-Macau Bridge, one of the world's longest sea-crossing bridges, utilized precast segments and launching girders to overcome the challenges of constructing over open water. Similarly, the Queen's Ferry Crossing in Scotland employed precast deck segments, allowing for rapid assembly and reducing on-site labor in challenging weather conditions. The Chenab Bridge in India, the world's highest railway bridge, also relied on precast elements due to the steep, mountainous terrain. The use of precast segments enabled engineers to build this bridge quickly and safely, despite the difficult topography and limited accessibility of the site. In conclusion, the use of precast, pre-stressed and post-tensioned concrete elements in bridge construction has revolutionized the industry by addressing structural challenges, enhancing safety, and reducing both time and costs. Supported by advanced machinery and precision engineering, this method provides a sustainable and efficient solution for building durable bridges that can withstand the demands of modern infrastructure. As technology continues to evolve, precast concrete will likely play an even greater role in shaping the future of bridge construction, enabling the creation of longer, stronger, and more resilient structures that serve communities for generations. The development of modern bridge construction has transformed dramatically with the advent of innovative technologies and advanced heavy equipment. Today, bridge construction is faster, safer, and more efficient than ever, thanks to advancements in methods and machinery that were once unimaginable, from impressive cable-stayed bridges to massive suspension structures, spanning vast water bodies. Modern bridge building is a testimony to engineering marvel and technological innovation. Central to this evolution are some of the largest and most powerful machines in the world, each playing a pivotal role in making these projects possible. In this extensive look at contemporary bridge construction, we'll dive into some of the fastest and most efficient bridge building technologies, as well as the enormous machinery that brings these designs from paper to reality. Modern bridge construction technology has introduced methods like precast segmental construction, which significantly shortens project timelines by casting bridge segments off-site before transporting them to the construction location. Once at the site, these segments are lifted into place, often by specially designed gantry cranes or launching gantries that can install entire segments in a matter of hours. This method not only reduces on-site work time, but also limits the environmental impact by keeping labor-intensive activities off-site. Precast segmental construction is now widely employed in building long viaducts, highway overpasses, and urban flyovers, especially in densely populated or ecologically sensitive areas. Another popular technique in modern bridge construction is the use of incremental launching, where a bridge is built in sections and gradually pushed out over supports. This method minimizes the need for temporary supports and is ideal for constructing bridges over rivers or difficult terrain. Incremental launching requires meticulous planning and precision, as each section of the bridge must be perfectly aligned before the next can be added. Specialized jacking systems and high-strength steel cables are used to push and stabilize these segments as they are launched. The precision and control involved in incremental launching allow for minimal disruption to the natural environment and existing infrastructure, making it a popular choice in challenging geographies. Heavy equipment such as massive crawler cranes and floating cranes plays a crucial role in modern bridge construction. These cranes are capable of lifting and moving huge bridge segments, some weighing hundreds of tons with remarkable accuracy. Crawler cranes are particularly essential in bridge construction due to their ability to handle heavy loads and maneuver around the construction site with ease. Floating cranes are also invaluable in projects involving bodies of water, as they can transport and position bridge sections without the need for additional support structures. These cranes are often custom-built to meet the specific requirements of large bridge projects, ensuring that they can operate efficiently in various weather conditions and challenging terrains. In addition to cranes, modern bridge construction relies heavily on specialized equipment like piling rigs, which are used to create deep foundations that can support massive loads. Piling rigs drill deep holes into the ground and fill them with reinforced concrete, creating sturdy support columns known as piles. These piles form the foundation of the bridge and are essential for its stability and longevity. The use of advanced piling rigs has made it possible to construct bridges in areas with weak soil or seismic activity, as the piles can be driven deep enough to reach solid rock or other stable materials. Bridge building has also been revolutionized by automated and semi-automated systems, which enhance both safety and efficiency on construction sites. Robots and remotely controlled equipment can now perform high-risk tasks like welding, painting, and inspection, reducing the need for human workers to operate in hazardous conditions. For example, some bridge projects now use drones for regular inspections, allowing engineers to monitor the structure's progress and detect any issues without halting operations. Drones provide real-time data and detailed images, which can be used to make informed decisions and ensure the project stays on schedule. One of the most impressive aspects of modern bridge construction is the precision engineering that goes into every phase of the project. Advanced software and digital modeling tools allow engineers to simulate the entire construction process before it even begins. This enables them to identify potential challenges and make adjustments to the design as needed, ensuring a smoother construction process and a more durable final product. In addition, GPS and laser-guided equipment allow construction teams to position each component with incredible accuracy, reducing the margin of error and increasing the overall safety of the project. In recent years, 3D printing technology has started to make its way into bridge construction, offering new possibilities for custom components and faster production times. With 3D printing, it's possible to create complex structural components that would be difficult or impossible to produce using traditional methods. This technology is still in its early stages, but it has the potential to transform the way we build bridges in the future. As 3D printing technology advances, it could lead to more sustainable construction practices, as it allows for the use of recycled materials and reduces waste. Some of the largest and most challenging bridge projects in the world today are being constructed using these modern techniques and machinery. For instance, the Hong Kong-Zhuhai-Macau Bridge, the world's longest sea-crossing bridge, was built using an array of advanced technologies and massive equipment. The bridge spans 55 kilometers and includes a series of artificial islands, tunnels, and cable-stayed sections. Constructing such a massive structure required innovative techniques to address challenges like strong currents, typhoons, and seismic activity. Another example is the Chenab Bridge in India, which is the world's highest railway bridge, standing at 359 meters above the riverbed. This bridge was constructed using incremental launching and heavy lift cranes, as well as special support structures to ensure its stability in the face of strong winds and potential seismic events. The Chenab Bridge is a testament to the incredible advancements in bridge construction technology, as it would have been impossible to build using traditional methods. Modern bridge construction has also benefited from advancements in materials science, leading to the development of high-performance materials that are stronger, lighter, and more durable than ever before. Materials like high-strength steel, carbon fiber composites, and advanced concrete mixes have become essential in building resilient bridges that can withstand extreme weather conditions and heavy loads. For example, ultra-high-performance concrete, UHPC, is now commonly used in bridge decks, as it offers superior durability and reduces the need for regular maintenance. Similarly, the use of carbon fiber reinforced polymers, CFRP, in bridge cables and other components helps to reduce the overall weight of the structure, making it more stable and easier to construct. One particularly exciting development in bridge construction is the use of self-healing concrete, which can automatically repair small cracks and prevent them from spreading. This technology relies on bacteria or chemical agents embedded within the concrete that activate when exposed to moisture, filling in cracks and prolonging the lifespan of the bridge. Self-healing concrete is still in the experimental stage, but it has the potential to revolutionize bridge maintenance and reduce the need for costly repairs in the future. The future of bridge construction looks even more promising with the advent of smart technologies and the Internet of Things, IoT. Many modern bridges are now equipped with sensors that monitor various aspects of the structure, such as temperature, stress, and vibration. These sensors provide real-time data that engineers can use to assess the bridge's condition and detect any potential issues before they become serious problems. This proactive approach to maintenance is known as predictive maintenance, and it allows for timely interventions that can extend the lifespan of the bridge and reduce the risk of accidents. To summarize, the combination of innovative construction methods, advanced materials, and cutting-edge machinery has revolutionized the field of bridge construction. Projects that once took decades to complete can now be finished in a fraction of the time, with higher precision and fewer risks to workers and the environment. Modern bridge construction technologies have made it possible to build longer, taller, and more complex structures than ever before, pushing the boundaries of what is possible in engineering. As technology continues to evolve, we can expect to see even more remarkable achievements in bridge construction, each one a testament to human ingenuity and the relentless pursuit of progress.